In this clip from RMDS Lab's 2020 I'm Data conference, we'll discuss the challenge of dealing with uncertainty in machine learning classification. You'll hear from Dr. Matteo Sessia, Assistant Professor of Data Science and Operations at University of Southern California's Marshall School of Business.
Hello, my name is Matteo Sessia. I'm an Assistant Professor of Data Sciences and Operations at the University of Southern California Marshall School of Business. Today I'm going to talk about a new method for estimating the uncertainty of predictions computed by machine learning algorithms for classification problems. This is joint work with my collaborators from Stanford University, Yaniv Romano and Emmanuel Candace. The problem is the following. Imagine we have a data set containing n independent observations, each consisting of a vector of p features and a label. You can think of this, for instance, as being a data set of images where the features represent the pixels for each image, and the labels are between 0 and 9 and represent the handwritten digit that is shown in the image. Our goal is to train an algorithm that can recognize the figures, that can recognize the digits, and can output a prediction for a new unseen image. So we can imagine that the new image is image n+1, and its pixels look like the ones here in the bottom left corner. And we're trying to guess what the correct label for that digit should be. And here I've chosen this example because it's not entirely clear whether that image should be 5 or 6. So there are actually a lot of problems where it is not possible to predict with absolute certainty what the label for a new example is. One must account for the uncertainty in the predictions. And even in a problem such as image classification, in which there is relatively little noise, it is typically quite easy for a human to recognize a digit, still there can be uncertainty. And it is important to develop algorithms for which the uncertainty is understandable. So specifically, our goal here will be to output a set of likely labels for a new test point instead of a single label. In mathematical terms, our assumption will be that the observations are sampled independent and identically distributed from some unknown distribution, which I denote as P of X and Y. We don't know what this distribution is. This is the data generating distribution, but we know that the available data and the new test point for which we want to make predictions are all sampled from this underlying distribution. Our goal is then to output a prediction set, which I denote here as C hat, for the new test point. And this set will, of course, depend on the features for that point, which we observe. The property that this set should satisfy is that we should be confident that it contains the right label for the new test point. And I'm going to denote the confidence level here as alpha. So if alpha is equal to 0.1, that means that we will be 90% confident that the true label for the future test point will be contained in the set that we output. And of course, it's important to make sure that these prediction sets are as small as possible. We don't want to return the full set of all possible labels because that wouldn't be informative. Instead, we want to try and compute the smallest possible set that will contain the true label with a certain degree of confidence that is specified by the user. In the previous example, ideally, we would like to return a set that contains 5 and 6. So how are we going to do this? Imagine for a moment that we knew what is the distribution of the data generating distribution. In particular, I would like to know what is the distribution of the label Y given the features X. Imagine then that I have an oracle which tells me what this distribution is, and let me denote by pi of Y of X the conditional distribution of the conditional probability of the label being equal to Y, the lowercase y, given that the features are equal to X. So this is the conditional distribution of the label given the features. And suppose for a moment that for a particular set of features, lowercase x, these conditional probabilities looked as goes in this plot. So this is an example where there are 5 possible values for the label y, and the most likely label in truth is the B label, the blue one, which is more than 50% likely to be the true label for this test point. Of course, normally we cannot observe this distribution. We cannot see these probabilities, but for a moment, bear with me and imagine that we can see these probabilities. Then how would we construct a prediction set with a desired coverage level, with a desired confidence level of containing the true label? What we would do is that we would sort the labels from the most likely to the least likely. And in this case, the most likely is the blue label, with the yellow label being the next most likely one, and so on. Then what we would do is that we would compute the cumulative distribution function of this distribution. What that means is that we would add all the probabilities up to the label we're looking at, following the ordering from the most likely to the less likely, to the least likely. So the cumulative distribution function evaluated for label B would just be equal to the probability of the label being equal to B, which is around 60% here. The cumulative distribution function evaluated for the label D would be equal to the probability of the label D plus the probability of the label B, and so on. And this is, of course, going to be equal to 1 once we reach the last label. So the curve, the black curve here, the increasing black curve is showing the cumulative distribution function. Since we know what the probabilities for the labels are in this hypothetical example, we can compute this curve. And then we will construct the set by including all the labels until the cumulative distribution function reaches 1 minus alpha. So if I'm interested in 90% confidence, I will look for that label for which the cumulative distribution function is above 1 minus alpha for the first time. In this case, with alpha equal to 0.1, the last label that I would include is label C. So my output prediction set with 90% confidence will contain the labels B, D, A, and C. The probability that the true label is one of these is larger than 1 minus alpha. And this is the smallest set that has probability larger than 1 minus alpha. In fact, we can construct a slightly smaller set by randomizing. So if we included the last label only with a certain probability and sometimes excluded it, we could still have this property hold with probability 1 minus alpha. So we could construct a slightly smaller set sometimes by randomly deciding whether or not to include C. But the idea is that if we want a deterministic set, if we always want to output the same set, it would need to include labels B, D, A, and C. Now, the difficulty here is that in truth, we don't know what these conditional distributions are. All we have is a data set. What we can do, however, is to use a machine learning algorithm to try and estimate what this probability may be.
If you enjoyed this video, check out the extended full talk on grmds.org. Use the link in the description to take advantage of a complimentary 1-month premium membership to our data science ecosystem where you can access online courses, webinars, datasets, workflow collections, and much more. Be sure to like and subscribe if you enjoyed this video for more content like this.